Hi, everyone, and welcome to our next presentation in the Your Universe series from the Brown Planetarium at Ball State University. I'm Dana Thompson, the director of the Brown Planetarium at Ball State, where we can usually recreate the night sky and see amazing things on our planetarium dome, including black holes. And today we're going to be hearing a lot about black holes from our visitor, our guest speaker, who is actually within the Department of Physics and Astronomy, which the Ball State Planetarium, the Charles W. Brown Planetarium here is a part of, Dr. John Millis. And John is going to be speaking to us today all about black holes, some interesting history about black holes, as well as some information about, are black holes represented in movies the way that we actually see them in real life? So help me in welcoming Dr. John Millis here today. I'm going to turn it over to John. So John, if you could unmute yourself, turn on your video. I'll go ahead and stop sharing my screen. And just so everyone knows, we do also have Rachel Williamson helping us out here today, answering any questions in the chat or getting some of the questions that you put in the chat to our visiting speaker here today, Dr. Millis. So without further ado, go ahead and take it away, John.
Thanks, Dana. I'm excited to be here this morning talking to you guys about black holes. Black holes are one of my favorite topics, particularly I've taught astronomy for a number of years, and black holes are one of those things that always just fascinated me and that I always love talking about in classes, because they're the types of things that students can really have a lot of questions about, particularly since they're represented in movies and in sort of other pulp culture. And so naturally people have a lot of questions, and they're just so exotic. They're different than anything that we would normally experience. So I kind of wanted to start at first just by talking about some history. If you're going to trace back the history of black holes, you obviously have to start with Albert Einstein. When he finally released his general theory of relativity in December of 1915, so over 100 years ago, there wasn't, obviously when he released it, there weren't any results or anything we really knew how to do with this theory. In fact, Einstein's theory equations are very complicated. They're nonlinear differential equations, and they're very complicated. And it actually took some time, almost a year before sort of even a single result was able to be pulled from those equations. And the person who actually did that was someone you may not have heard of, named Carl Schwarzschild. And what Schwarzschild was able to do with Einstein's field equations is he was able to find the place around a gravitational body where the escape velocity would begin to exceed the speed of light. And that was the first sort of real solution that had ever been found using general relativity. However, it didn't seem to have much utility. No one really knew what to do with it. But of course, we now know that this sort of laid the foundation for thought around this concept around a black hole. The idea of a black hole actually dates back hundreds of years, even back to the 16th century, where this concept that you could have a gravitational mass in which would be so intense that light could not escape. But of course, it was just a sort of theoretical concept. There was no mathematical framework for it, but still there was this sort of just idea out there that such a thing could exist. But Schwarzschild's work really kind of put the first mathematics to that, or at least relativistic mathematics to that in the early 1900s. But that's kind of where it stayed for about 50 years. It wasn't until the 1960s that there was any sort of renewed interest in what this might mean, any implications to what we now today call black holes. And this all emerged because people were starting to take measurements of things like microquasars in 1963. And in 1967, Andrew Hewish and Jocelyn Bell first discovered the pulsar, or rapidly rotating neutron star. And these are compact objects. These are objects which have such extreme densities that they manipulate the environment around them in very dramatic ways. And I know that you guys have been talking about neutron stars for the past week or so, so I won't rehash any of that at this point. However, just to say that 50 years in between, there wasn't a lot of interest in neutron stars and black holes, even though there was some sort of developing theoretical framework around them, because these objects were so extreme, so small, that it wasn't believed we'd be able to detect them even if they did exist. So they were just kind of relegated to some interesting theoretical exercise that had sort of no impact on scientific or astronomical theory. But then, of course, what we found in the 1960s was that not only is it possible that these things exist, but we should be able to actually observe them in various ways, and particularly in the way that they interact with their surrounding environments. The next person I want to mention is someone named Roger Penrose, and his work really focused on how you would create a neutron star or a black hole in the first place. And again, 1960s, they started talking about what would happen when a massive star reaches the end of its life. And so these are stars that are at least several times the size or mass of our sun or more. And when they reach the end of their life, their behavior is different than most stars in the universe. Most stars, like our sun and even smaller, reach the end of their lives and they move into what's called a red giant or red supergiant phase. And they begin to push off the outer layers of the star and form ultimately what's called a planetary nebula. Massive stars, though, like I said, those that are at least several times the mass of our sun or more, undergo a slightly different process. So all stars, in order to sort of maintain their size and sort of shine the way that we normally think of stars shining, they are converting hydrogen into helium in their cores. Well, as they get older, eventually they start using all of that hydrogen, and they need to now start burning heavier and heavier elements, starting with helium, okay? And they're undergoing this fusion process with heavier elements. And as this happens, it causes the star to transition into different phases, different types of objects, specifically like what we call a red giant or a red supergiant or a pulsating yellow giant. And so as it goes through this process of fusing heavier and heavier elements, the star starts changing its size and its properties until eventually it reaches a point where the star becomes unstable. And it happens at a very special point, actually, when the star begins to fuse iron in its core. I don't want to go into the technical details now. If you have questions about it at the end, I can go over it. But the idea is that the fusion of iron is what's called an endothermic process. So is where you would fuse hydrogen to form helium. When you fuse the hydrogen atoms together, it actually releases more energy than it takes to bring the atoms together. When you get to iron and heavier elements, it actually takes more energy to bring them together than is what is produced through that process, which means there's a net loss of energy, which means the star can no longer be stable, okay? And it starts to collapse in on itself. Now, when this happens, a chain reaction of events happens. The core of the star becomes very compressed, and the outer layers of the star begin to fall down onto that core and eventually reflect off. And these shock waves get created that actually blow the outer layers of the star apart. So if we look at this animation, you can see this happen. So the star is at its stable point, but then as it began to collapse, it blew out the outer parts of the star. And all of that heat and energy in the outer parts of the star carry those outer layers of material out, and they glow red hot. Now you'll notice here in this image that there's still something left behind. And what you're seeing, that glowing ball in the middle, isn't the star as it once existed, but rather the remnants of the core, still glowing white hot. Now, in this case, there's two possibilities of what can happen. You'll either end up with a neutron star, which we've been talking about for the last week or so, or if the star is massive enough and the environment in that core was extreme enough, it could collapse all the way down to a black hole. So I'm actually going to switch my screen here. Just give me a minute. All right. So what we have here is what we call a active black hole, okay? Now, when you see black holes represented in TV and film, this is usually the type of thing you're thinking about, particularly the recent movie Interstellar. There we go, sorry. The movie Interstellar showed something like this. So this is a similar animation to what you would have seen in that movie. And even though the black hole, which you can see visualized as just the dark circle or sphere in the middle, is visualized, you can actually see radiation coming from the environment around it, light, because of the interaction of the black hole with its surrounding medium, okay? And so as we kind of move this around, you can see the different parts and you can see it rotating. If I kind of move over here a little bit, you can see this gas over here, okay, that is circling around the black hole. Because of the gravity of the black hole, it's pulling that material in and it's compressing it to a very high temperature and it's causing it to radiate, okay? Now this radiation, okay, we can observe here on Earth in the form of X-rays or radio waves and things like that. You'll also notice that the space around the black hole is being warped. So you see this distortion, okay? This is not some issue with the animation. This is actually trying to represent the impact that the black hole has on the surrounding area. It's literally that light gets distorted because of the intense gravitational energy of the black hole. That light gets distorted around it on its way to Earth, okay? Now, those distortions are actually kind of hard to see in some cases, in many cases. In some cases, we can actually measure that distortion and learn information about the black hole because of that. But typically when we observe black holes, what we're observing is the radiation that is actually coming from this disk, this compressed material around the black hole. We'll talk more about the properties in a little bit. But first, before we do, oh, it's not letting me go back. Oh, here we go. Okay. I want to talk about a slightly different type of black hole. So before, when we were talking about the history of black holes, I mentioned that sort of 50-year period where there wasn't a lot of interest or work being done on black holes because partially there was a belief that even if they did exist, which it wasn't clear that they were actually physical objects that could exist in the universe, because they are so extreme, the physics of them seems to fly in the face of what we typically know and understand of how objects work in the universe. And of course, part of this was this transition between classical physics and relativistic and quantum physics that was happening in the early 20th century. But one of the things that was really at the heart of this was this idea that even if black holes existed, would we be able to even observe them? Well, one of the reasons that's a challenge is because unlike the image I just showed you, where the black hole is interacting with the environment around it, pulling gas in around itself, heating that gas, and causing that gas to glow hot so that we could observe that glow here from Earth, many black holes are what we call inactive. They are not interacting with their surrounding environment, which means they simply just look like holes in space. And particularly since most of them are so far away that they would be very, very small, we have really no hope of seeing them. Now in this visual here, you can see in the middle where the black hole is and the impact it's having on the environment around it. Basically is the light from the background object, in this case, sort of the galactic band, is trying to pass around the black hole. That light gets distorted. But unless you're pointing your telescope at a very specific spot, that distortion would be almost impossible to measure from here on Earth, okay? We really only can detect the presence of black holes by the impact they have on objects around them, okay? Not just by the warping of light, because that's usually too subtle for us to measure here on Earth, so far away from where the black hole is located. So, how do these black holes fit into the grand scheme of things? Well, we talked about black holes are really the result of what happens when a massive star reaches the end of its life, okay? So When all stars die, they will typically become one of three types of objects. Stars like our sun will become a white dwarf, which you can see represented here on the bottom left part of this chart. And these are typically small. They have the mass of our sun or less, typically, sometimes up to about 1.4 times that. And then you have neutron stars, the next step up. Now, these are stars that are a bit more massive than our sun. We'll leave these behind. But the most massive stars in our universe will leave behind black holes. And these are what we call stellar mass black holes because they're on the order of about several times the mass of our sun up to 100 times or so the mass of our sun. And these objects exist in all the galaxies around the universe, and they're just the result of massive stars that have died. However, we've also seen a different class of black hole, what we call supermassive black holes. You can see represented on this chart at the far right end. And these black holes are millions or billions of times the mass of our sun. Now, what's interesting here is you'll notice there's a huge gap in between. Either black holes are sort of some multiple of the mass of our sun, a few times the mass of our sun maybe, or they are millions or billions of times the mass of the sun. There isn't a whole lot in between. And that's kind of an interesting question, right? Why do we not see this so-called intermediate mass black holes in the universe? Do they exist and we just don't see them? Or is there some reason that we only see small black holes or really, really big black holes? And one thing that we should note about supermassive black holes is that they really only exist at the cores of galaxies. And the prevailing theory is that these supermassive black holes are formed as part of the galaxies themselves. So when a galaxy is forming, the formation of this galaxy, as it's beginning to come together, the central part of it becomes really dense, and all of that matter gets compressed together and ultimately forms a supermassive black hole. But you also have a little bit of a chicken and the egg problem, right? One of the questions that scientists have asked is say, okay, if supermassive black holes are associated with galaxies and their formation, does the creation of a supermassive black hole then lead to the creation of a galaxy? Or is a supermassive black hole the result of a galaxy being created? Which causes which? And that's a question we don't really have an answer to. There's a lot of theories out there about how that might work. But typically, these supermassive black holes are part of that galaxy formation. There aren't, billion solar mass stars that are exploding and leaving these supermassive black holes behind. That's not what's happening. They're being formed by the sudden accretion. And what that means is a bunch of material being pulled into an object at once. That accretion of material, of a lot of material all at once during the formation of a galaxy to create these supermassive black holes. So how does a black hole work? Well, what I have visualized here is a black hole that is interacting with surrounding medium. There is material that's being pulled around it. And typically what will happen is that this material will come from another star. So it's not uncommon in the universe. In fact, it's quite common to see black holes interacting with other stars. That's because typically stars tend to form close to other stars. Our solar system is actually a bit different in that regard, that we only have a single star in our solar system. Many solar systems have multiple stars. So when one of those stars reaches the end of its life and explodes in a supernova and forms a black hole, it still could potentially be interacting with another nearby star. Well, because of the intense gravitational energy of the black hole, if the black hole is too close to that star, it'll begin pulling material off of that star into a disk around it. And as I said before, during that process of pulling that material into what we call the accretion disk, that material becomes hot and it begins to glow in various wave bands of light, like X-rays and radio and other things, and even optical. So what you're seeing here is this material that gets pulled into a disk. Now you might be looking at this and saying that doesn't really look like a disk. It looks more like a hat sitting on someone's head. And again, that's because of the extreme gravitational environment of the black hole. the disk is really flat around the black hole, okay? But as the light, so if the black hole is kind of in front, like towards you, when their disk comes behind the black hole, the light from that disk is going up. But the gravitational energy of the black hole bends that light. So it looks like it's coming over the top of the black hole, even though it's going behind. It's basically an optical illusion created by the intense gravitational field of the black hole, which makes it look like it has this odd shape. You'll also notice, for instance, that one part of the, or one side of that disk looks brighter than the other. Again, that's not by accident. What you're actually seeing is the fact that as the material is coming forward towards you, it gets what's called Doppler boosted, okay? And so ultimately the light looks more intense and is actually going to be shifted more towards the red end of the band, okay, as it gets compressed, like it's coming towards you, or sorry, blue shifted. And then as it goes around the other side, okay, the light gets more spread out. It's moving away from you and being pulled away from you. And so it actually looks less bright and is also going to be spectrum shifted as a result. Now, interestingly, this visual also looks similar to what you would have seen in the movie Interstellar. However, when they originally shot the movie or created the visuals for it, they had this Doppler boosting effect as part of that image. And when they showed it to test audiences, the test audiences didn't understand it. They didn't understand the Doppler boosting effect and why one side looked brighter than the other. And they thought it was a problem with the visual itself. And so the filmmakers went back and made it look more uniform in its brightness around it, even though that's not what the science said should happen, just because it would be more visually appealing for the film. So even though they knew the way it should be represented, because black holes are so weird and we're not used to thinking about these Doppler boosting effect or Doppler beaming effects, because that's not something we often experience in a visual way particularly, that they changed it for the film just to kind of make it more palatable for those of us that don't have as strong a scientific background. Again, just one other thing I wanted to mention, you'll notice that we have in the middle, it basically just looks like a black abyss. There's nothing in there in the middle. And that's again because the intense gravitational energy is so strong as you get closer to the black hole, to what we call the event horizon, that not even light can escape from the black hole at that point. So once something crosses that boundary, it can't come back out again. So can we actually see black holes? Well, as I mentioned before, there's things that we have been able to detect, and more specifically, we've been able to see how black holes have actually interacted with their environments. The effects that they have on maybe nearby stars. So if we see a star that has a very peculiar motion around a central point, okay, around something we can't see. So something is gravitationally influencing that object in a very strong way. That's evidence that there could be a black hole there. Also, as I mentioned before, we've seen black holes interact with their environments in very strong ways to produce really bright radiation, particularly like an X-ray or gamma ray or in radio. And those interactions that we see are indications of the presence of a black hole. But that's not the same as actually imaging the black hole itself. That takes a lot of extra work. And so it actually wasn't until last year, 2019, that we were able to first fully realize an image of a black hole and its accretion disk. So what I've shown you here is images that were generated as part of the Event Horizon Telescope system. And it's a series of radio telescopes that were observing a galaxy called M87. And this is the supermassive black hole, as we talked about, billions of times the mass of our sun, that is in the central part of this galaxy. And the presence of that black hole, which is the dark spot in the middle, is superheating the gas around it. So you can actually see for the first time where the black hole is located, and you can actually see the stream of hot gas around it. Now, there's a few things I want to say about this. This is a very challenging measurement to take. Number one, this galaxy is 1 billion light years from Earth. right? It's really far away, which means it's also very, very small and very difficult to see. So what they had to do is when you want to see a dim object, you need a really big telescope. The dimmer and more difficult the object is to see, the bigger the telescope that you need. The problem is that we lack the capability to build a single telescope big enough to see something like this in this level of detail. But scientists are clever. And so what they did is they actually came up with a technique that allows them to have a whole bunch of radio telescopes all over the world, and they all look at the same object at the same time, and they can combine their data together. And it acts as if you had one giant telescope almost the size of the entire Earth. But you don't. You have a bunch of smaller telescopes all working together, okay? So they were able to do this, and they were able to take this data, and you can see how the image changes over time. You can actually see the flow of the hot gas in the disk as it's going around the black hole. Now, piecing all of that data together is a huge challenge, right? Because you have data from all these different telescopes saying different things, and you need to figure out a way of actually piecing that data together to represent the image, right? And so the physicists working on this project brought in some really smart computer scientists. And so if computers are your thing, maybe you don't really like physics, or you're not that interested in astronomy, but you really like computers, you can still contribute to our broader knowledge of the universe and to astronomy by working with astronomers on projects like this. And so one of the scientists, Katie Bauman, she used her computer programming skills along with several other people that were working on her team. And they were able to figure out how to piece the data together to actually visualize what this black hole looks like. So this is sort of the first, like I said, representative image of what a black hole will actually look like in the universe as it interacts with its environment. And of course, now that we have the technique down, we can begin to look at other black holes, hopefully even the supermassive black hole in the core of the Milky Way galaxy, the galaxy that we live in, and try to see something similar. Though there's a lot of stuff in between that makes that measurement actually really difficult to do, but we're going to try. So I want to just kind of address maybe some fun questions that you guys might have. And so these are some that I came up with in collaboration with Dana and Rachel to think about what you guys might have questions of. And one of the questions that I've gotten a lot is, what would happen if the sun became a black hole? So this is a little video of kind of a fly into our solar system. You can see the sun in the middle, and if you look really closely, you can see the rocky worlds, including the Earth orbiting the sun. And as you come out, you can see Jupiter and Saturn. So our sun is one solar mass by definition. And so what would happen if our sun were suddenly collapsed into a black hole of the same mass? Okay, think about that for a second. Make a prediction of what you think would happen. And let's see what happens as we roll this forward. Oops. So as the sun begins to compress down, okay, and form into a black hole, you see it shrinking, becoming much more dense. It's the same mass, but just much more compact. And you notice that really nothing happens to the orbit of the planets. Oops. Sorry, it's not. Right? The planets are still staying in their orbits. Okay, the sun is gone, which means we've lost the light source and the heat source that we rely on, obviously, to support life on Earth. But nothing happened to the planets. They didn't get sucked all of a sudden to the center of the solar system, right? Well, why not, right? That's usually what people first think of. They think of, well, black holes, right, are so intense. They have such intense gravity that not even light can escape them. So how is it that the planets orbiting our sun wouldn't get sucked in to the center of the solar system if the sun suddenly became a black hole? The reason is that the influence that the sun has on the planets is because of its mass, not because of its density, right? So if it were converted into a black hole at the same location, there would still be the same amount of gravitational mass, pulling on the planets towards the center of the solar system, which means nothing would change. But there is one key difference. When the sun shrank down to a black hole, it went from being really, really big to really, really small. And what that means is that you could get then closer to the surface. So the difference would come as you actually cross that boundary of where the sun used to be to now where that black hole is located. Because you can get so much closer to the surface of the black hole, it'd only be a couple miles across now. You could get really close to it, and that's when you would start experiencing the difference in that gravitational energy, because now you can get so much closer to where all that mass is concentrated. But back out where the planets are, we wouldn't notice any gravitational difference or change in our orbit, okay? We would obviously be getting a lot less, heat and light, so there would be some dramatic changes there, but in terms of our orbit, nothing would change. Another popular question that I get a lot is, what about wormholes? Because this comes up a lot in science fiction, right? So you see where a black hole exists somewhere in the universe, and some team of explorers stumbles upon the black hole, and for whatever reason, they get too close and they get pulled into the black hole, right? And it transports them to some other part of the universe or some other point in time, right? Well, is that actually possible? Is that something that could happen in the universe? Could a black hole be used to transport someone through time and space? Okay, well, it's a good question. And this is actually something that Einstein explored as a concept when he was thinking about black holes. And the idea is that black holes are so intense that they basically create what's called a gravitational well in space-time, okay? So, because if you fall into that well, it just keeps going down forever. You can't ever climb back out of it, right? And that's why we talk about nothing being able to escape the black hole. But it must lead somewhere, right? It can't just be infinitely deep, right? Does it ever actually connect to somewhere else? So what you're seeing in this visual is sort of a representation, if you will, of that funnel of basically how things could fall into the black hole, and then they would just kind of keep going down forever. Well, one of the things that they thought about was what would happen if you had this well that actually then connected to another point in space. Could something fall into a black hole and then be spat out somewhere else in the universe or at a different point in time, okay? And this is what we call a wormhole. You see them represented in movies and stuff like that all the time. Now, what Einstein developed was, and that other people have built on since then, is that if you have a rapidly rotating black hole, it could create such a bridge across space, okay, such that it could connect these 2 points. However, there's a challenge there. In order for that wormhole to be stable, that bridge between the 2 points to be stable, nothing could actually pass into it, not even light. As soon as a single photon of light, or a single ray of light, if you will, passed into that bridge, the bridge would collapse in on itself, okay? They're completely unstable. Scientists have made attempts to try to get around this in different ways. They said, well, what if you had an exchange of energy? What if you had stuff flying the exact, basically identical light particles flying opposite ways through the bridge at the same time? Could that work? Or what if we found a way to make negative energy, right? And you passed the normal energy in with the exact same amount of negative energy to cancel it out at the same time. Well, there's little tricks you can do like that to try to like get around this problem, but pragmatically, there isn't anything that we're aware of or any sort of way that we could design a solution to take advantage of this wormhole property. So scientists basically said up until this point that wormholes can't naturally exist in the universe because they would be completely unstable and they wouldn't actually allow anything to pass through. Even if they could open up for a brief moment, they would collapse in on themselves as soon as anything approached the wormhole. So unfortunately, that's probably not going to be in our future as a means of transport around the universe, but you never know. So I wanted to have an opportunity for questions. I know Rachel and Dana have been monitoring the chat, so if anyone submitted any questions, we can talk about that. Just real quickly, I wanted to talk about this image. You may recognize this from the movie Interstellar, one of my favorite movies. And this image was actually sent to me by Kip Thorne years ago. I gave a talk about the science of Interstellar, and he allowed me to use some of the visuals that they had used in the movie for that talk. So I just wanted to show that here in case anyone had any questions related to these black holes and accretion disks and any related. So I'll kick it back over to Dana to see if anyone has any questions or if there's anything else we want to talk about.
All right, thanks so much, John. That was amazing. Really exciting stuff. Black holes is definitely one of the topics that our audience loves to hear about. So let me go ahead and stop sharing your screen so we can really chat about some of the questions coming in. If you do have a question, put it in the chat and we'll get it to John here. But I, of course, have some questions. And one of the questions that is asked at the beginning of one of our most popular planetarium shorts, the Black Hole music video with Morgan Freeman auto-tuned. So that usually excites people in the planetarium. People love that song, but the beginning of it asks scientists who are really good at answering questions about black holes. They ask, what are black holes made out of? And I understand that that's a really hard question to answer because when you get near a black hole, physics just does not act the way that we're familiar with, right? Mm-hmm. So that kind of changes the way that the material would exist. And so it might be some sort of material that we're just not able to comprehend easily. So do you have any thoughts on what black holes are actually made out of at that high density?
Yeah, that's actually a really great question. And this is something that was when I first started learning about this and thinking about what even matter or material is in the universe. It's so mind-blowing that it just got me so excited. And really the thing you have to go back to is Einstein. One of Einstein's most famous mathematical expressions is E equals mc squared, right? And what that means is that matter and energy are equivalent. They're different forms of the same thing, right? And in special circumstances, we can take pure energy like light and convert it into matter. This actually happens around us all the time. As high energy radiation hits our atmosphere, it produces electrons and positrons, right? Literally converting light energy into matter. You can do the reverse process as well. I take an electron and a positron, it's antiparticle. I bring those particles together, they combine, they annihilate, and they produce pure energy, right? So we tend to think of matter and energy, light, being different things, but they're actually just two forms of the same thing. So as a black hole begins to form and all of that matter is actually crammed together, right? The properties that make matter, right? The actual individual properties of those particles begin to become lost, right? They break down, right? And instead, you're starting to intermix this idea of matter and energy to the point that they're indistinguishable with each other. So really what a black hole is it's a region of space of such intense energy density that it's no longer really matter or energy. It's energy in the sense of just like the concentration of energy in the universe. And it's literally just deforming and reshaping the universe around it because of how intense it is. But it's not, you can't really think of it as even being like particles anymore because there aren't any individual particles left at that point. They're now indistinguishable from just normal energy. And this actually leads to a whole nother like question about black holes, right? Because we define black holes by their mass and their spin, and then sometimes they're another thing we call their charge if they have an imbalance in charge. But if I have two black holes, and we'll call them A and B, and they have the exact same mass and the exact same spin and the same charge, they are literally indistinguishable, right? There is no way to tell one apart from the other. So if I did a shell game and mixed them around and said which is which, it would be literally impossible to tell. They would have no distinguishing features. And that's one of the things about black holes that's really difficult to get our mind around, because as soon as you cross that event horizon, that point where energy can't escape, that also means that information can't escape from the black hole either, which means that anything about what's going on inside the black hole, anything about its particular makeup or composition gets lost. We can't extract anything out of the black hole beyond that point. And therefore, if I have two isolated black holes, right, so they're non-active, I can't tell them apart if they have the same mass and spin, because those are the only things that I can actually tell about a black hole.
That's completely wild. It's really hard to kind of understand, and I understand that we're still trying to answer a lot of questions about black holes. One of the questions coming through the chat here is from Brent, who visits the planetarium all the time with his family, and his son is wanting to know if wormholes are real.
So as we talked about, wormholes are really interesting sort of theoretical constructs, right? There's some fun things we can do in physics that we can produce a result, right? A mathematical result of something. To say like, well, there's nothing that means this is impossible to exist, right? However, that doesn't mean it actually exists, right? It's just a consequence of the mathematics. One example of this, it's maybe a little easier to sort of understand than wormholes, although maybe not, is when you construct the special relativity equations for energy. They're actually a sum of squares. So when you find the energy equation, you have to take a square root. Well, anytime you take the square root of a number, you get a positive root and a negative root. So whenever you're analyzing a system, there's a possibility of getting a positive energy, but a negative energy. What does that negative energy mean, right? It comes out of the mathematics, and we know the mathematics works. Like it explains the physical world around us. We put our relativity equations, we hardwire them into our satellites to account for relativistic properties. So we know that they work, but then we get this weird result where it says that I should have negative energy, but we don't experience negative energy, right? So just because I get a mathematical result that says something doesn't mean it's actually physical to the world or to the universe, okay? It's the same sort of thing with wormholes, right? Wormholes are a mathematical consequence of our physical understanding of black holes, for instance. And they wouldn't necessarily have to be tied to black holes, but black holes would be the sort of place that they could naturally arise if they did exist. But again, that doesn't mean that they're actually real. It's a mathematical construct based on some properties of black holes. But that doesn't also mean that they don't exist either. But if they do exist, like I said, we have a big problem we'd have to get around with how we exchange energy through the wormhole, because that would have to be balanced. Otherwise, the wormhole collapses in on itself. So that may be one of those questions we never get a definitive answer to, whether this is just a consequence of mathematics, of just the way that we've put the equations together to try to explain the physical world. You sometimes get these sort of weird results, or if it is a representative of something physical in the universe, but even then it would be pretty limited.
Yeah. So do wormholes exist? Maybe, but we haven't found them yet. Not in space anyway, right?
Right. Well, a naturally occurring wormhole you could travel through would not exist, because that would collapse in on itself.
Okay.
So you wouldn't be able to travel through a wormhole if they did exist. But there's also no evidence that they do exist that I know of.
Yeah, observational. That's interesting. We have a lot of other questions coming through here. So let's move on to the next one from Jessica. Her son, Peter wants to know if neutron stars will ever form black holes. And they ask because they don't remember what a neutron star is. So can you give us a brief reminder of what a neutron star is, and will they ever form black holes one day?
Great question. This is one of my favorite questions that I ever get in my astronomy class. And again, so when stars die, they typically form one of three types of objects: either a white dwarf, a neutron star, or a black hole. Okay. There's some other sort of weird things that can happen. The core can explode and leave nothing behind. And then scientists have also predicted that there could be another fourth option out there called a quark star. But again, we have no observational evidence that those exist. But And in which case they would be similar to a neutron star in most ways, just even more dense. So we typically focus on those three: white dwarfs, neutron stars, and black holes. And really, these are the cores of the stars that are left behind when the star dies and blows itself apart, either to form a planetary nebula or a supernova. And what happens is the core begins to collapse in on itself because the gravitational energy is so intense that it just starts contracting, okay? And when it was a star, because of the nuclear fusion that was happening in the core, it prevented the core from collapsing. It was a balance, what we call hydrostatic equilibrium. The outward radiation pressure produced by the nuclear fusion was balanced by that gravitational energy. But once that nuclear fusion energy is gone, basically because it's become an endothermic process, like I mentioned before, there's nothing to balance that gravitational energy and it starts to collapse. Now, really, what type of object will be produced depends on the mass of that core, okay? So initially when it starts to collapse, the atoms in the core become squished together, okay? Now, if you remember what an atom looks like, you have a nucleus, protons and neutrons, surrounded by electrons orbiting around it, okay? Now, of course, that can get really complicated when you start getting into the orbital shapes and all of that, but just for simplicity, we'll think of it as kind of a sphere, okay, for now. But if you have these spheres that are being compressed together, these basically electron clouds going around a nucleus, these electron clouds are bumping into the other electron clouds and they're becoming compressed, okay? That actually creates a pressure, what we call an electron degeneracy pressure, that the electrons around an atom can't be pushed any more towards the nucleus, okay? So it becomes harder to push those atoms closer together, okay? That's actually what leads to the formation of a white dwarf. Those atoms get compressed, so it becomes really dense, but that pressure created by the electron clouds of the atoms being squished together stops it from collapsing any further, okay? But then when you get beyond a certain mass, which is about 1.4 times the mass of our sun, the pressure becomes so intense, the gravitational energy is pushing on these atoms so much that it can actually cause those electron clouds to collapse, and it pushes those electrons into the nucleus, which is normally a big no-no, right? That you don't want that to happen. And so you go through a process of what's called neutronization. The protons in the nucleus absorb those electrons, and they actually convert into neutrons. So those atoms that were normally protons and neutrons surrounded by electrons all get squished together into a big ball of neutrons. So now these atoms that were like this with these electron clouds get squished down to just the size of the nucleus. Well, now you have a whole bunch of extra space, right? Because most of an atom is empty space. It's this tiny little nucleus surrounded way out here by these electron clouds. And now they're all just in the nucleus. So now you have all these balls of neutrons, right, that now can be squished together, okay? So now the white dwarf shrinks down, right, and can become a neutron star, which is basically a big ball of neutrons, okay? It's actually more complicated than that, as we talked about, because that pressure is so intense, you actually start getting some pretty exotic things that happen, and even the neutrons themselves break down in the core, but that's getting into some real weirdness. But you basically now get an even more dense object. It's a big ball of neutrons, okay? And the reason it doesn't collapse further is because these neutrons now, right, are being squished together, and they want to stay being individual neutrons, right? They have kind of a boundary to them, right? And so the energy, the pressure of those neutrons pressing against each other, what we call the neutron degeneracy pressure, meaning that it's keeping those neutrons being individual neutrons, okay, and not being squished together any further, causes the object to stiffen and it becomes a neutron star. But here's the thing, like we were able to overcome that electron degeneracy pressure, you can also overcome that neutron degeneracy pressure. If I add more mass to my neutron star, right, such that I get to the point where that neutron degeneracy pressure is not enough to stop those neutrons from being pushed and squished together to now starting to occupy the same space, that the object will then collapse into a black hole. And that's really why I was talking about earlier, that this idea of what it is, what kind of matter it's made out of, doesn't even make sense anymore because you have now overcome all of the properties that make particles particles. They no longer exhibit the properties of a neutron or whatever, right?
Yeah.
You've
And it kind of
lost
seems,
all of that because they're so compressed together.
yeah, and it seems interesting that we would go from a neutron star directly to a black hole without having that quark star in the middle.
So
From my
the thing
understanding of
is that the
'cause-
difference between the neutron degeneracy pressure and the quark degeneracy pressure, and for those of you who don't know what quarks are, so neutrons and protons are made up of 3 quarks each, which is even more subatomic particle. But the neutron degeneracy pressure and the quark degeneracy pressure are actually very similar. So to get a quark star, you would have to have just the right amount of mass, right? Just enough to overcome the neutron degeneracy pressure, but not so much that you'd overcome the quark degeneracy pressure. And that's why even if they did exist, they'd be exceedingly rare because you'd have to get that amount of mass just right to get it to actually be stable, which is why it's unlikely they exist at all. And even if they did, they'd be really rare. So.
All right, so we have a lot more questions to get to. Lenny wants to know if the Earth telescopes from, I'm assuming the Event Horizon Telescope project, if the Earth telescopes could link with space-based telescopes to form an even larger telescope equivalent.
Yeah, actually, one of the things they've talked about doing, so my background is in gamma ray astronomy, not radio astronomy. So I don't know as much about what the future plans are for kind of like future projects like that. But one thing that has been discussed was building telescopes on the moon, because then you would have telescopes on Earth, telescopes on the moon, and then now the size, what we call our effective area, is really big, right? Because the moon is 250,000 miles away from the Earth, right? So now you have this really big area of coverage and you could improve your angular resolution, basically the detail of these really tiny objects. You could improve that greatly if you had moon-based telescopes. I know that's something they'd love to do, but of course, as soon as you start talking about building things on the moon, the cost goes way up. And so I don't know what the status of those future plans are, but it's something they've talked about for a long time. And not just for radio astronomy, but also other things like optical astronomy and things like that. So linking terrestrial or Earth-based telescopes to non-Earth-based telescopes is something that we have talked about and that's been proposed for a long time, but we don't really have any good examples of where that's happening right now. Radio astronomy is really challenging because the longer the wavelength of light, the bigger telescope you need to see it. Radio waves are the longest wavelengths of light that we observe, which means radio telescopes have to be really, really big. So putting something really, really big in space or on the moon is going to be really expensive because now you need really big rockets to put all that stuff up there, or you have to send it up in lots and lots of parts, which means you need to have lots of missions, and then you have to figure out a way to assemble it in space, and that's really difficult and really expensive. So I don't know that we will see such projects in the near future, but long term, that would really give us a peek into some of these really extreme environments in the universe if we could build some of those systems on the moon and then take advantage of that distance.
And we're really fighting against gravity with that one. And so speaking of gravity, as we have been this whole presentation, Trey wants to know, can black holes be detected in the future based on gravity directly instead of by the gravity's effect on light? So I'm assuming they do go into mentioning that gravity is a big part of what makes black holes powerful. And over the last couple of decades, there have been a lot of scientific studies to detect gravity. So I'm assuming they're talking about maybe gravitational waves. So in the future, can we detect black holes perhaps just by the effects of gravity and not so much on the light that is affected by that gravity?
Yeah, you're still actually making the detections based on a black hole interacting with something else, typically a second black hole. But what you're doing is that you're getting basically mismatches in gravitational energy. So as two black holes spiral towards each other, they both have such intense gravitational energies that you get these massive warpings of space, right? And so kind of imagine, being in a tub of water really still and then taking your hands up and down like this, right? As you create these disturbances, you start sending waves across the bathtub or the pool or whatever it is. So as two black holes get close to each other, their interacting gravitational fields create these massive disturbances in space-time, and they send ripples across the universe. Those ripples can be detected by gravitation experiments like LIGO and other things. But you're still relying on one black hole typically interacting with a second black hole, or at least something else that's really massive that has a strong gravitational field, like maybe a neutron star or something like that. But all the detections, and we've only been able to really start making these detections to a high precision in the last 5 years or so. And so we're still only seeing dramatic examples. So very large stellar mass black holes, that are like 50, 60, 70 times the mass of our sun, two of them interacting. And there aren't a lot of those in our galaxy particularly. So we haven't seen a lot of examples of that, but we're starting to be able to make those types of detections. And as our experiments get better, we'll be able to see sort of smaller and smaller ripples, and until the point where we could maybe start seeing types of effects like what you're talking about.
Yeah. So you answered part of one of the other questions here, and Rachel got a great answer on the chat too, to Lenny, wanting to know what black holes, if black holes can collide with each other, and if so, what would happen. But would it be correct to think that they just merge, like the larger one takes in the smaller one, or the more massive one takes in the less massive one, and then they create an even larger black hole? And perhaps this is why we see supermassive black holes in our universe.
Yeah, so they would be very energetic events, that's for sure. There's a type of event in our universe called a gamma ray burst. And this is an intense emission of really, really high energy light. So gamma rays particularly, but would also signal a very large gravitational wave emission. And we believe that at least some of those events, these gamma ray bursts, are associated with colliding neutron stars. Colliding black holes would be even more intense and release even more energy. So again, we have to kind of change our thinking of like what a black hole is, because it's not a ball of anything, right? We tend to think of them because we see this sort of spherical shape. What we're seeing is the boundary at which light can't escape, right? But it's just basically a well of energy, of concentrated energy focused in a single point in space. That's why we call it a singularity, okay? And so as these two black holes would begin to merge, right, it's really a combining of their energy. But because of the way that they would do that, as they begin to circle around each other and get closer, there's a bunch of mismatches of these energies that are colliding, right? And so it begins to actually pull things apart, and you get this energy exchange. And you would also, because of the interactions of their magnetic fields, you would get basically kind of like a beam of energy that would be created and kind of shot across the universe, typically in like a single direction.
So that's interesting, because black holes, we can measure the mass of them, and they do occupy a certain area of space. At least their event horizon extends so far, right?
Right.
And they can get more massive over time by taking in material, right?
Yes, but again, when we talk about mass, it doesn't necessarily mean matter, because E equals mc squared. So there's more mass, but it's really just more energy. Right?
Okay. So the two kind of energies would combine in the way that you just described.
Yes. But they would also, because of that collision, they would release a bunch of that energy as well, right? So some of that energy would actually be ejected as part of the collision.
Okay. Yeah. So. And gravitational waves, does that dissipate some of that energy?
Yeah. And so like energy can't be created or destroyed, it just changes form. And so energy can be taken away from a system in the form of light or gravitational waves. All of that is just different forms of energy, kind of being pushed out of the system as part of that collision. Does that kind of make sense?
Yeah, absolutely.
Okay.
I'm looking at the other questions coming in here, and Jessica wants to know more about degeneracy pressure.
Okay.
If you can maybe explain what that is in 2 sentences
Yeah,
for someone who does
sure.
not know anything about it.
Yeah.
The
So
challenge. I'm going to challenge
again,
you.
all degeneracy pressure really means is that 2 things cannot be pushed together any more than they are, because it would then change the structure, the shape of the atom in a way that's not allowable, right? So atoms, you have a nucleus and then the electron orbits, right? I can't, for instance, it'd be a violation to put 3 electrons in the first orbit. It can only contain 2. So so the degeneracy pressure means that if I pushed any harder, it would force that electron into an orbit it's not allowed to be in, right? So that's what it means by degeneracy. There's only certain combinations that are allowed, certain structures that are allowed, and if I push harder than that, I would then begin to overcome that structure, and it would collapse, basically. And so it's the degeneracy pressure is basically the pressure, basically how it resists being broken, if you will, and being forced into like not allowable shapes. So, but at that point, when you're talking like electron degeneracy pressure, right, you're talking about an atom being pushed so hard it is no longer an atom in the way that we think of it, right? It has been, that structure has been broken due to how much force you're putting on it. That was more than 2 sentences. I'm sorry.
It's okay. We'll make them 2 very long run-off sentences. So that's perfect. There's a lot of great comments in the chat, and if you have any questions, put them in the chat. We'll try to get them answered after the event today. I do want to ask one of the most popular questions that we get, and that's, can we explore black holes up close? And when we are exploring black holes, we found that the nearest black hole to us is about 1,000 light years away, which is still very, very far. So can we ever explore them up close?
So it depends what you mean by up close, because it would be difficult to get, because they are so far away, it would take too long to get to any black holes that we know about. When I say we know about, I'll come back to that in just a second. But you could, in theory, you could send a probe if we could get close to a black hole somehow, right? So we'll just say we can somehow overcome the space, interstellar space travel problems and figure out how to travel to other stars. If we could figure out how to do that, hypothetically, then you could send a probe towards a black hole and you could have it beam back information to Earth, okay, to tell us what it's seeing. Eventually, though, it'll get to a point where it crosses that event horizon, and it can't send information back anymore because the information just falls back into the black hole. So we could get close to a black hole, but once you start approaching that event horizon, you'd no longer be able to send information back, and we wouldn't be able to learn anything anymore. There is, I should say, there's also some cool things with that. If I'm watching a probe approach a black hole, what'll happen is that I'll see it approach the black hole, and then from my perspective, it'll look like the probe just freezes, okay? And that it's just stuck there in space. It's not, it's continued to fall into the black hole, right? But because once it gets to that event horizon point, light can't escape. The light basically starts just echoing off of that point. And you are seeing what looks like kind of like a picture, a snapshot of the probe as it goes across the event horizon. Now, over time, it'll fade. It'll get like lighter and lighter and lighter until it fades away as the rest of those photons, right, echo off the event horizon, and you won't see anything anymore. But it just looks like it gets to a point where it freezes and then just fades, is what you would see if you were watching this probe approach the black hole. But also there's another weird thing that happens. There's one of my favorite scientific terms is called spaghettification. And what that means is that as an object approaches a black hole, right, So let's say that I have a spacecraft, a space probe or something that's approaching a black hole. As if this side is approaching the black hole first, and this is sort of the back end, as it approaches the black hole, this side is going to be pulled more strongly than this side, right? And this is true on Earth too. Technically, your feet are pulled towards the Earth more strongly than your head is. So when you're standing on the ground, your feet are pulled a little bit more than your head, okay? Now, it's such a slight effect on Earth, we don't really notice it on a day-to-day basis, okay? But a black hole is so extreme that effect is significant. So even though, so this side is being pulled more than this side, it starts stretching it out, right? Not only that, but because the gravitational energy is coming in like this, because it's such a small point in space, the gravitational energy is coming in this way. It's not only pulling you in, it's also squeezing you. Okay, that's kind of hard to show without a really good visual, but the idea is that the object would be stretched and squeezed until it was just basically a stream of particles falling into the black hole. And we call that spaghettification, which is a great term. So.
Yes, astronomers are really great at naming things. They kind of name things how they are, right? Like there's a huge spot on Jupiter that has been going on for hundreds of years. So let's just call it, and it's red. So let's just call it the Great Red Spot. There's an object in space that's dark. You can't see it, but it might act like a hole. So let's call it a black hole, right? They just name things how they are. And we could be talking all day today, I'm sure, about black holes. Again, there's a lot of great conversation in the chat here, but I'm going to go ahead and end the program here. But if you do have a question, you're watching this later, put it in the chat. We'll try to answer it after the event here today. But thanks so much for watching, everyone. And thanks so much, John, for explaining a lot about black holes, more than I have heard about in a long time. So it was really, really great. Thank you so much.
My pleasure.
All right, so next week we're going to be finishing our Your Universe series with a presentation on the early universe with Dr. Michael Scobie. And I'm going to be presenting alongside Michael for that one. We're going to be exploring things like the quark gluon plasma and what that really is, or what we think it is anyway, and how we can explore it in environments here on Earth that we've created. So actual scientific experiments that represent the conditions of the early universe, which is really difficult to do, but we're able to do it. Well, again, thank you so much for joining us. Next week, check us out on Friday. We're back on Fridays at 11 a.m. Thanks so much for watching, everyone. Have a great rest of your day, and stay tuned for even more posts about black holes on our Facebook page.